In this lecture, we will consider recycle. And we've actually done some problems, but you have not, we've only looked at them in portions. So now you should be able to complete these calculations, including drawing your flowchart. And the best way to get good at this is to practice. So you're encouraged to practice additional problems from the back of the chapter. So you're going to be handling your reactive recycle processes similarly to non-reactive. As usual, you perform the degree of freedom analysis around each unit. First, calculate with the around the units where you have 0 degrees of freedom, and note that the overall balance includes only fresh feed to the process and products leaving the plant, so coming in and going out of the plant. And here we're going to learn how to compare single pass conversion and overall conversion. Let's look at an example calculation. Methanol is produced by reacting carbon monoxide and hydrogen. A fresh stream containing CO and H2 joins a recycle stream, and the combined stream is fed to a reactor. The reactor outlet stream flows at a rate of 350 moles per minute and contains 10.6 weight percent H2, 64 weight percent CO, and 25.4 weight percent methanol. Notice that these are weight percentages. This stream enters a cooler in which most of the methanol is condensed. The liquid methanol condensate is withdrawn as a product, and the gas stream leaving the condenser, which contains carbon monoxide, hydrogen, and a small amount, 0.4 mole percent. Now, you're going to be writing this as a mole fraction, and be careful when you do that. Remember that percent you divide by 100. Uncondensed methanol vapor is the recycle stream that combines with the fresh feed. So here's the chemical reaction. There's only one chemical reaction. How many independent species? Only 2 atomic species. There's 3 molecular species. So let's replace all of the weight percent numbers in the reactor outlet stream with mole percent. So we're going to do that first. Convert all of these mass fractions or masses to moles, and you can have mole fractions. Okay, now let's draw and label a flowchart for the entire process. And we've already seen this as an example, that when you have a recycle stream, combining with the fresh feed, okay, we have recycle combining with fresh feed. This stream here has a different composition, so you should write it in such a way that you can put numbers on it. Here we know everything about the stream. Here we have some methanol, but some methanol is coming out in this one, so that's going to require a little bit more calculation. So here we are writing streams as number of moles versus total moles and mole fractions. Okay, this one is a mole fraction, mole fraction, mole fraction. Here these are written as total moles, moles per minute. So these are molar flow rates, and here's a molar flow rate. Here is a molar flow rate, and these are the mole fractions, but with the molar flow rate, these can easily be converted into mole flow rates. Okay, so the easiest way to deal with this is to write things in terms of the molar flow rates. So if we do the degree of freedom analysis, okay, if we do the degree of if we consider the balances around the condenser and the overall. Around the condenser, we have N3, N4, and X. Okay. Now around, let's look back at the flow chart here. All right. If we draw the overall balance, okay, before we do any calculations, we actually have 3 unknowns. We have N3, N1, and N2. Okay, so here, in fact, this is copied out of the solution manual. It's assuming that we already have N3, okay, because we're going to calculate N3 around the condenser. And then we are going to do the overall process. Okay, so if we do the balances around the condenser, we're able to calculate N3, N4, and X. I would urge you, you've got this solution here, practice this. Write these balances on your own without looking at the solution, and then see if you can get these numbers. Okay, and then we can perform the overall balances and get the inlet fresh feed composition. And now we can look at the all the information that we have calculated. We have calculated all the missing information. Now we ask ourselves, do these numbers make sense? Okay. Well, we're feeding in this, and we're getting out methanol. And all of the hydrogen is being recycled and being reconverted. So in this sense, the numbers make sense. And we have a tiny amount of methanol going back in. So we have a tiny amount of methanol here. And so these numbers do make sense. So we can calculate now the single pass and overall conversion of carbon monoxide. And we know the equation is moles in minus moles out divided by moles in. Okay, so here we calculate the single pass conversion only around the reactor. So moles into the reactor minus moles out of the reactor divided by moles into the reactor, we get 25%. What about overall? Well, moles into process minus moles out of the process is, we have 32 moles of CO going in. There's no CO coming out. So we have an overall conversion of 1. Now, if we have a case where there's a purge stream, the purge stream is necessary when we have an inert, because what happens is that the inert is going to simply go around and around and build up in the system. So to summarize this, we treat these similar to processes without reaction. You identify the control volume where you can have 0 degrees of freedom. And remember, if you're going to do molecular balances, that you have to include generation or consumption terms when there's a chemical reaction. Single pass conversion includes only the conversion in the reactor, and overall conversion is the conversion of the complete process. So this is the problem, and I'm going to put it in your homework calculation. And some of this is going to look familiar, actually. So you have some answers already. This is the one that we've already done. Okay? And so you should be, you're well underway to do this. So I'm going to include it with the homework, not as a video quiz.